So thank you very much, Dr. White, for agreeing to talk to me today. We might as well jump right in. I think the thing we could do for our viewers and listeners that would be most useful to begin with is for you to tell them what fusion energy is and how that differs from standard nuclear energy. Just like a rationale for the pursuit of fusion energy and a place and placing of it in the proper context with regard to our pursuit of advanced energy and reliable energy supplies.
Right. So fusion is the process of fusing together the most abundant and the lightest element, hydrogen, into heavier elements. So it actually changes the element. And this is the process that powers the universe, because it powers all stars, including our own sun. And you can think of a star, our own sun, it's a big conversion factory. It's like a standard burner in the sense that it takes the huge masses of hydrogen that the sun is made out of, and in the center of it, where the conditions meet the requirement for fusion, it converts the hydrogen into helium, and by that process, releases staggering amounts of energy per reaction. Usually when I comment in public about fusion, it's like, so fusion makes life possible in the universe because it's the radiant heat that comes from stars that makes life possible in a place like the planet Earth. So it is you think of it, it's the quintessential or fundamental energy source of the universe. That's the starting point. So it distinguishes, why is it such an effective energy source? It's because it changes the element, right? So what happens is that if you take the mass of those starting particles of this before you fuse them together, they have larger mass than the particles that result from this. And you go, but how can that be? Because we all learned in school that mass cannot be destroyed or created. But this is what Einstein realized, was that in fact mass and energy are the same thing. And then when you convert them in these processes, you end up with energy. And it's hard to imagine how much of a different process this is than either fission or standard chemical reactions, which is basically what we run the world on today. And in terms of comparing it to chemical energy, the average energy released per reaction or per mass of particle is about 10 million times larger. That's amazing, right? So this is why stars on our own sun can last for 10 billion years. I mean, there's an enormous amount of hydrogen in the sun, but if it was running on a chemical process, like burning hydrogen, like you would think of in a fuel cell or something like that, it would only last for a few thousand years. It lasts for 10 billion years. That's the difference between them. And with respect to fission, it's actually, there's a relation there in the sense that fission changes the elements as well too, but it's literally the opposite process. Fission, as the name implies, splits apart or fissions the most unstable, heaviest elements that exist, like uranium. And again, by this equivalent of energy and mass, it releases energy, but it's a completely different physical process. And then we can discuss a little bit more about what that means, but that at the starting point, you can say, the universe already voted. Fusion is the energy source of the universe. Just the question is, how do you actually harness it on Earth? And the consequences of harnessing it are very different than either chemical or fossil fuel energy or standard nuclear energy.
Now, you said that it's in the deeper reaches of the sun that the fusion reactions take place, and the sun is extraordinarily large, and the conditions there are very much unlike the conditions on Earth. So what are the conditions under which fusion becomes possible, let's say, on the cosmic landscape? And then how is it that those might be duplicated? How is it even possible to duplicate those on Earth? And also, how is it possible to duplicate them on Earth without things going dreadfully wrong?
Right. Yeah. So the conditions in the set. So I'll take it varies from star to star. Actually, there's nuances to the differences in different types of stars, but I'll take our own sun as the example. It's the easiest one. So as you imagine, like in the center of the Earth, like we learned this in elementary school, like there's different layers to the Earth, right? You have an outer cold crust, and as you get towards the center, because of the pressure exerted by gravity, and the core and the mantle, these are all higher temperature, and they're much denser because they're under so much pressure. The same thing happens in the sun, which is actually larger, much larger than the Earth. And what you can think of is as you go from the surface of the sun, which has got is in contact with outer space, so it has minimum pressure, and it's actually the coldest part of the sun, so at around 5,000 degrees. And as you start going towards the center of the sun, the temperature keeps increasing, the pressure keeps increasing, and eventually, when you reach the center of the sun, it's approximately 20 million degrees Celsius in the center of the sun. It's under those conditions that basically the fusion reaction can start to occur in significant quantities. And that's what's required for a star to essentially ignite, is that there is sufficient conditions of particularly temperature and pressure that allow enough fusion reactions to occur that it starts to keep itself hot to allow other fusion reactions to occur. So this is interesting, is that there are entities, even our own solar system, which didn't quite make it to stars. So there's actually an Arthur C. Which one was it? I think 2010, right? Arthur C. Clarke, brilliant scientist and writer, postulated that at the end of that story, you might remember that Jupiter is turned by the aliens into another sun in our solar system. That's not quite totally possible, but it is interesting. Jupiter basically has a very similar composition to the sun. It just didn't get quite big enough and hot enough in the center to start triggering enough fusion reactions to make it a star. So what this means is that fusion occurs naturally only really in one place in the universe, and that is in the center of stars, because that's the place where you can get the conditions of particularly temperature that allow it to remain hot enough to be able to sustain the fusion reactions. And quickly, like why is that needed? It's because this process of pulling the hydrogen, pushing them together to fuse, means that you have to overcome extraordinarily large forces which don't want them to get close to each other, which is a basic force of nature. So it's the electromagnetic force, because the electrical repulsion between those two particles doesn't want them to come together. So you have to have high average energy to essentially overcome that barrier and get them to fuse. So you can think of, like, we use analogies like you have to have your match or your kindling hot enough to get the big fire started. Well, in this case, you sort of have to get enough average temperature or energy to start up the reaction and to get it going. So those are the requirements.